Good afternoon, colleagues. I wish you a hearty welcome to our side event on safety standards. And I would like to check with our speakers who are presenting remotely whether they can hear us and show their faces. We all are used to this format. It's a hybrid format this time, but instead of flying them in, they were not available for the entire OEWG. So we choose this hybrid format, profiting from our acquired experience over the last 2 years. We decided to organize this side event because this year it is on the agenda of the Montreal Protocol. It is on the agenda of the Montreal Protocol since the negotiations on the Kigali Amendment. The Dubai pathway identified a number of key issues for parties having doubt about the feasibility of HFC phase down and safety concerns enabling or being an obstacle to the use of flammable refrigerants was a main concern to be resolved. In the decision 28/4, which was adopted together with the Kigali Amendment, the parties recognized the importance of a timely updating of international standards for flammable low global warming potential refrigerants, including international standard IEC 60335-2/40. To support actions that allow for the safe market introduction, manufacturing, operation, maintenance, and handling of zero GWP and low GWP refrigerants that are alternatives to hydrofluorocarbons and hydrochlorofluorocarbons, HFCs. So on this basis, we continue to work. The year later in Paris, we agreed in close cooperation also with the Chinese delegation. We proposed jointly a decision which required the Ozone Secretariat to inform the parties via their website on developments of the relevant safety standards which could enable and could support the implementation of the Kigali Amendment. That was 2017. And the decision requesting the Secretariat to provide regular updates of this information has an end date, and that is this year. So at the MOP, we would need to decide whether this exercise was useful and whether we would like the Secretariat to continue this exercise for at least a couple of years. So it's not only for this reason it's timely to have this workshop. Also, other concrete progress has been made. In particular, by updating relevant standards, but also the EU was active domestically. We mandated our European standardization body to look into this issue and to review existing standards and complement and propose to complement them where necessary. But we also funded research and project looking into the real risks of using flammable refrigerants, in particular also concerning or to evaluate the risk of the real risk of leakage of such equipment with such substances. Broadly, that will be those will be the three main topics of the presentation we will see. And also another one complementing analyzing the potential benefits of applying the newly updated standards. With that, I would hand over to our first speaker.
Thank you.
Perhaps you could present yourself quickly.
Can you see my screen?
Yes, we can.
Perfect. Second. Yeah. Thanks for the invitation to present the project at this meeting. My name is Britta Petzold. I'm based at the Heat Company in Germany and coordinated this project together with our technical expert Daniel Colburn, who unfortunately cannot join the meeting today. Heat Company is active in the area of climate change and sustainable cooling and heating since several years, and this was one of our project focusing on the safety standards. Live Front project was funded by the LIFE program of the EU, and FRONT stands for Flammable Refrigerant Options for Natural Technologies, Improved Standards and Product Design for their safe use. So to briefly give you an overview on the project goals, the project aimed to remove barriers posed by standards for flammable refrigerants in refrigerant, air conditioning and heat pump applications, and to increase the availability of suitable alternatives in RUG HB applications by improving the system design to address flammability risk, and by encouraging the use of climate-friendly alternatives to fluorinated gases. The project.
Sorry for interrupting, Britta. Are you sharing your slides?
I thought so.
I think we can only see your video.
Oh. Can you see the?
Now we
Perfect.
can.
Now we can, sorry. Shall I go back one slide or?
Perhaps that would be useful simply to, the slides will be later on also uploaded, but it would be useful to give the participants directly an impression.
So for everybody, as the FRONT is not easy to understand. FRONT stands for Flammable Refrigerant Options for Natural Technologies, Improved Standards and Product Design for their safe use. and the project goals to remove barriers posed by standards for flammable refrigerants in RUG-HP applications, and to increase availability of suitable alternatives in RUG-HP applications by improving the system design to address flammability risk and by encouraging the use of climate-friendly alternatives to fluorinated gases. The project started in mid-2017 and ended mid-2020, 2 years ago. But the project website is still online, so if you visit livefront.eu, you can find all the background information and details. The project consortium consisted of 6 partners. Project leader was Checo. Then we had the European Coalition on Standards. EAT was responsible for the work on leak hole sizes and risk assessment. And in the consortium were 3 manufacturers, NIBE and AIT, 2 heat pump manufacturers, and AHT, a refrigeration cabinet manufacturer. So the focus of work and achievements can be split into 3 project phases. In the first phase, we focused on a literature review to understand better which safety standards are relevant for the sector and associated barriers related to refrigeration appliances, air conditioners, and heat pumps. In a second step, we did a field study and laboratory tests on leakages and related mass flow to provide real-life detailed data on leak hole sizes, underlying causes and their frequency, as well as the resulting patterns of the refrigerant mass flows and concentrations in different settings, because this is really where there was a lack of information. And in a third step, we defined recommendations. So building on all the lessons learned from the field study and our laboratory test, we focused on improving product design together with the 3 manufacturers by making modifications to current practice with the goal to accommodate for the use of larger hydrocarbon charges. And we evaluated options for passive and active risk mitigation measures. So getting back to the first phase of the project, the literature review, Checo revised existing safety standards at international, European, and national level. And the findings of this study demonstrated that primary barriers to flammable refrigerants and safety standards are mainly related to the refrigerant charge size limits, because these limit the ability of systems to provide the desired cooling capacity. But the study also showed that efforts to review the current charge size limits for flammable refrigerants are and were underway within several standards, and we will hear one example later in this meeting. So let's start at the beginning. The charge height limits were identified as one of the main barriers, and we focused on getting more information on leak rates, worked on housing geometry, system tightness, airflow, and the risk of ignition with our work. The focus was on leak hole sizes and leak mass flow rates, because The correct determination of hole sizes is essential for handling flammable hydrocarbon refrigerants. Often the charge sizes are or were based on worst case scenarios, but if you base on these catastrophic leaks the safety requirements, the equipment will potentially be over-engineered with excessive costs, with a probability of occurrence of such a leak being extremely minimal. So a balance has to be found. If the determination of the hole size is too small, you underestimate the potential hazard. If it's too large, products are over-engineered and overpriced. So the correct determination is essential. And as you can see in the figure, there's a relationship between leak hole size and the extent of zone 2, where protected electrical components need to be applied, and the minimum room area necessary to avoid flammable concentration. So the larger the leak hole size, the greater the mass flow into the space and the higher the chance for developing a flammable concentration. So what was done in our field work under the Live Front project, we collected around 1,000 leak samples in small and medium RUC HP systems, and the leak rate was measured. We covered a variety of system types, from heat pumps, air conditioners, and refrigeration cabinets, different ages and different installations. On the slide, you can see some samples that were tested. And compiled all the results in a report on recommended leak hole sizes and also in an online database. So here you can find all information gathered on leakage sizes, the leak simulation, concentration developments, types of leaks, causes of leaks, development rates, with, for example, the most common leak type being the forced rupture leak. I have to add that not only data gathered under the Front project, but also findings from previous work under GSZ Proclima compiled in these databases. You can find them online and get more information. I just want to present you the main outcomes of this work. So when we looked at the probability distribution of leak hole sizes, learned that the vast majority of the leak holes reported from the field are very small, less than 0.1 square millimeters, so much smaller than previously assumed. And this trend from the field test that larger leaks only occur in exceptional cases was also confirmed by the long experience of our industry partners, the 3 equipment manufacturers. If we have a look then at the probability of leak mass flow rate, we learned that around 90% of the holes had a release rate of lower than 10 grams per minute. And this is important information because the assumed refrigerant leakage mass flow rate is one of the most critical parameters affecting the development of a flammable concentration and thus the determination of refrigerant charge size limits. key points from our research. The leak holes were found everywhere, one can say, in the appliances, low and high pressure sites, main components, piping, etc. And what we also saw that was the hole size does not vary notably with system age, size or capacity of the system, or the refrigerant charge. In the last phase of the project, we focused on improving the product design and did concentration measurements. Each of the three manufacturers tested one prototype with R290. So we had one refrigeration cabinet, one air-to-water heat pump, one ground source heat pump, which were all tested with different levels of leak rates and in varying situations, including the application of mitigation measures to determine if the leaks result in dangerous concentrations of the refrigerants. For this purpose, rooms were built to simulate an average utility room, and the room was fitted with an array of gas sensors to determine the concentrations of R290 at different locations and in varying distance from the source. And on the picture, you can see one of the prototypes, the prototype of an indoor package air-to-water heat pump installed in the mock utility room. For the test, it was determined that the concentration of R290 surrounding the product should not exceed 50% of the lower flammability level. And it was also noted that in the case that any of the heat pump's parts may contain one or several ignition points, the same 50% of lower flammability level should not be exceeded. So the aim of the test was to demonstrate that an efficient design or adaptive mitigation measure can be implemented to ensure a safe usage of the flammable refrigerant in the heat pump equipment installed indoor, independent of the refrigerant charge size and independent of the room size. And we also wanted to define an efficient and robust methodology that can be used to evaluate whether a heat pump equipment using a flammable refrigerant can operate without compromising safety. This figure, you can see how the test was set up. So the heat pump was composed of 3 zones: the hydronic unit with the hydraulic and electrical unit, the condensing enclosure with the refrigerating circuit except evaporator, the evaporating enclosure, and zone Z representing the surrounding of the heat pump where the R290 concentration shall not exceed 50% of the lower flammability level. The rest dots indicate where the gas sensors were located, and the orange arrows show the release position of the R290. And the test was run with different release rates, and for all 3 tests, 500 grams of R290 was released. Conclusions and outputs from the field study and the testing. Our tests showed with all 3 prototypes that effective mitigation measures are available to allow for higher charge sizes for the application of R290 in the tested prototypes. And based on our test results, new approaches to determine safe charge limits were proposed, including experimental methods, calculation methods, and risk assessment methods, and new approaches to determine charge limits will enable a far greater and wider application of hydrocarbons without resulting in a substantial increase in flammability risk. So results from this project were already fed into the discussions of the safety standard working groups and were also used for proposals of charge size calculation and leak simulation tests in the -40 standard that Asbjørn will present a bit later. All findings are also summarized in our report, shown here on the slide. In the next step, we focused on quantitative risk assessment on RUG-HP equipment. So legislation in Europe demands that products are safe, and implementing a quantitative risk assessment leads to a better understanding of those parameters that contribute to risk and weaknesses in the system in different activity phases. So it's an estimation, very useful to consider the uncertainties associated with each element in the product. The figure on the right shows some of the points that need to be addressed, like the identification of explosion hazards, determination of the likelihood of occurrence of a hazard, the identification of ignition hazards, estimation of possible effects of an explosion, and evaluation of the risk. As we had seen in our work, in the previous work packages, the probability of occurrence of a catastrophic leaks is extremely low. So if safety requirements are developed assuming the more realistic case of pinhole leaks, it's very likely that minimal changes to the equipment design are required to accommodate flammable refrigerants, compared to those that need to be taken for non-flammable refrigerants. To list some of the effective mitigation measures like system with integral airflow, charge leak test methods, improved housing design. And each of the manufacturers run one exemplary product risk assessment for their respective prototype, where they identified hazards and then analyzed the associated consequences and related design options for all the product activity phases. You can see the example of the ground source heat pump used for testing. So they designed a specific setup. They made the compartment containing the refrigeration circuit very tight, so to ensure that in case of a leak of refrigerant, the amount of the refrigerant released in the upper compartment of the heat pump and also in the room where the heat pump is installed will be small enough so that no flammable atmosphere is created at any point. And their option chosen was to evacuate the refrigerant outside the building. Outcomes from all three risk assessments were that the flammability risk presented by the use of hydrocarbons is, compared to the fire risk associated with other equipment and appliances, relatively low. And what was really interesting to see was that identified analyzed hazards for all three appliances showed that these often arise from human errors or misbehavior. Thus, effective mitigation measures to reduce the risk are one, detailed and easy to understand instruction manuals for the technicians, and well-trained technical personnel for installation, commissioning, and decommissioning. And on the other hand, hermetically sealed leak-tight systems to prevent the formation of an explosive atmosphere within and surrounding the appliance in case of a leak. The results from our work are relevant to various safety standards. So they were and are being fed into the committee's working group discussions. I listed several of the standards of interest as EN 378, ISO 51449, IEC 60CC 5-2-89, and the last one will be addressed by Asbjørn in his presentation. Some final remarks and lessons learned from our work. First of all, it was not easy to get commitment from industry on leakages and product design. So a transparent discussion was difficult because they consider this information to be confidential. What became clear is that the industry is capable to implement solutions with natural refrigerants that meet safety targets. But what we also learned is that they will only do so if this is required by sufficiently stringent policy requirements on F-gases. So ambitious GWP limits, excuse me, and also the discussion on chemical substances as PFAS under the REACH regulation. From market side, we need financial incentives to support the further investment in and the uptake of the climate-friendly technologies. And within the standard committees, stronger support for civil society organizations to engage in the discussion would be beneficial to allow for equal voting in the committees, and it would be necessary to undertake measures to enhance the updating timelines of the standards so that they are in line with climate and environmental targets. All the information and the reports I addressed in my presentation are also available online, so included the relevant links for you so that you can get back to this later. And with this, I would like to thank you for your attention. If you have further questions, please get in touch.
Thank you very much, Britta, for this comprehensive presentation of this very relevant piece of experimental practical work. I would open the floor for a couple of clarification questions, if any. So if someone would like to address a question, please use a microphone, otherwise Britta cannot hear it. So far, I do not see any requests for the floor. So with that, I thank you again, and I would come to the next presentation, providing a general overview of the newly revised standard IEC 60335-240, which was explicitly mentioned in the decision accompanying the Kigali Amendment as key for opening the path for equipment alternatives to HFCs with low or no GWP alternatives. I give the floor to Asbjørn Fonside, who shares the respective working group. And Asbjørn, the floor is yours.
Thank you, Cornelius. Yes, I'm going to talk a bit about the new edition of -2-40, the air conditioner and heat pump and dehumidifier safety standard. First, a very brief introduction to myself. Asbjørn Montiel, I'm a consultant, but what's important today is I've been leading the work on developing the new edition 7 of -2-40. And going forward, I'll be chairing the steering committee that takes responsibility of -2-40. Right. So we have this new edition 7. As I mentioned, it's the safety standard for air conditioners, heat pumps, and dehumidifiers. And most importantly, it enables flammable refrigerants in many applications by increasing the allowable refrigerant charge. Today, I'll focus on the A3 refrigerants, but there are also larger charges allowed for A12. The proposal applies a combination of mitigation measures together with increased charge limits, so that even though we put in more refrigerant, we actually do not get a more unsafe system. Normally, we actually get a more safe system, even though you increase the charge limit. Just very briefly, the mitigation measures we have incorporated, many of which, by the way, were investigated in the Live Front project, are releasable charge, so only the refrigerant leaked out of the appliance is creating a hazard. It's airflow. If you can mix, once the leak gets out of the appliance, if you can mix it with the air, then you can get below a flammable concentration. And the last is increasing the or what we call enhanced tightness, which is doing measures to make sure that any leaks will be small. And again, that links up to some of the things Britta talked about regarding the Live Front project. Good. So why did we start this? Well, back in 2015, there was a wish for, actually from especially China, to be able to make split air conditioners and reversible splits systems with propane specifically. But when they looked at the charge limits, they could see it is possible to do these systems following the old standard with A12 refrigerant. But if you want to apply propane, then for small rooms, that means small air conditioners, it is possible with the old standard. But for larger rooms, the old standard simply didn't allow enough refrigerant to deliver the cooling capacity needed. And no manufacturer wants a production or a product range where only the small part of the, or where the small part of the range use a different refrigerant than the large part of the range. So this started the discussion, and we ended up creating a working group to address A2 and A3 refrigerants. So this working group, we met first time September in London, and then we met every 2 to 3 months. We ended up with 500 documents that we've been reviewing and discussing. We had 50 experts from 15 different countries, and a total of 17 meetings in this group. And by mid-2018, we merged the work with the working group that had been working on A12 refrigerants. And then by mid-2019, we decided to move the work to a new working group. And instead of just looking at hydrocarbons or flammable refrigerants, we looked at how to get the next edition published with all this new work. So we had a new working group. The number of experts expanded a little bit, 55 experts from 17 countries. We managed to get through 520 documents in this working group. Again, some of this coming from the Lifefront project. And we, to get through all this, we actually had to meet every once a month. And of course, early 2020, we had to convert to web meetings due to the Corona situation. But in 2020, we got the first draft out for the first vote. And then here, late 2021, we finalized the work of the what we call the FDIS, the final draft ISO standard. It was out for vote here in the spring, and it passed. It actually passed without opposition, which tells you that there's a lot of industry players who feel that they need this standard. So even though I'm sure you can find mistakes in it, all the players in the industry seem to conclude that, yes, maybe we want something a little different, but we really need this standard now. And it was published 25th of May this year. From a European point of view, we still have a process in front of us to develop an EN version, and that's going to take 2 to 3 years. We need to develop the national deviations. Actually, we already have a draft of that, but there is a process for this to be approved, and that's likely to take 2 to 3 years for various reasons. And by the way, in the US, you have a UL version of the standard, which is under development. And they might actually be a little faster than EU in this case. So, charge limits. The idea is that safety needed to be at least as good as the previous edition. And for A3 refrigerants, we very much linked the larger charges with additional mitigation measures. And there we have to keep in mind that the current charge limits are actually 20 years old. They were released back in the early 2000s. The upper limits in a room is actually not changed. It's still 988 grams. If you're outdoors, it's still 4.94 kilogram of propane. What has changed is that with the additional mitigation measures, it's actually practically possible to use them in a reasonably sized room. So before we had these upper limits, but in reality there were things in the standard that prevented you from going anywhere near these charges, and that has been addressed. One point which is not covered by our standard is competence of service technicians. We have an EN standard on this, and it is in the process of being converted to an ISO standard. And it is definitely a topic worth paying attention to, especially for service people who are used to working with non-flammable refrigerants. It is worth considering. So the first mitigation or group of mitigation measures are the releasable charge concept. The amount of charge released to the occupied space can be limited by adding mitigation measures. And there are various options. You can do a refrigerant pump down, you can have safety shutoff valves. And actually, the way we do it in the standard, you can also come up with new concepts. And the idea is it's only the refrigerant that leaks that creates a hazard. And we have a test, relatively simple test, where you run the system for half an hour, then you simulate a leak for 4 hours, and then you measure what is left in the system. And if you can come up with a concept that can somehow limit the releasable charge, then that's fine. Here on the right, there's a small graph with, it's actually more like, it's a thought experience. It's not a real system, but it could be. If you take a a system with approximately 1 kilogram of flammable refrigerant, then in reality, it's not all going to be released once you puncture the system. So maybe 15% is going to stay back. But if you have a split air conditioner for cooling only, actually 80% of the refrigerant is in the outdoor system. So by simply having 2 valves on the pipes going indoors, you can easily release this, or easily lower this. In this example, we said, okay, 450 grams. In reality, you can probably go lower. Right? So especially for split systems, this is an extremely efficient way of limiting risk. Airflow. Once we have a leak, we always have a flammable atmosphere around the leak. The current safety standards are actually based on the idea that a leak will go into a room where there will be absolutely no air movement. So the leak will flow down from the unit, hit the floor, and we want to limit the charge so that we don't get a flammable atmosphere at the floor. Once you add a fan to the system, you can start mixing the leak in the whole room, in the air of the whole room. And therefore, you can leak a lot more before you get a hazardous situation. And we have a new approach in the standard based on jet theory. And that has been verified with both CFD, lots of CFD simulations, but also physical experiments. And I believe some of this work is actually under from the Livefront project. Enhanced tightness. We saw in the Livefront project how the expected hole size in a system affects how much refrigerant you can leak into a room before it becomes dangerous. And the reason is that once you start leaking refrigerant, you get a flammable atmosphere just around the hole. But if you allow enough time, then this refrigerant will simply dilute into the air in the room and get below the flammable limit. If the leak is very slow, you can leak a lot because it'll dilute a lot before you get a hazardous situation. If you leak very fast, you're going to get a flammable atmosphere just around the appliance, and you'll get it very fast. So a large leak means you cannot have as much refrigerant leaked before you get a hazardous situation. We added additional construction requirements to lower the worst case leak rate. It's a concept that has already been applied for A2Ls, but is now extended to A3 refrigerants. And it results, for instance, in lower requirements for airflows or high accepted charge sizes. So now it gets a little bit more nerdy, but to help companies apply the standard, I've developed an Excel sheet, and you can find it using this link. And please share; it's free to use. And the idea is that once you read through the standard and you realized, okay, I want to do a system. Let's say I want to do a system enhanced tightness, this additional design requirements, and I want to have a fan in it. So, for instance, a split system. Then this Excel sheet incorporates all the formula from the standard. So you can quite easily play with your concept. Let's say I want 450 grams of propane. The minimum room area, let's say I want to set it to 12 square meter. So that's going to be the stuff I write on the packaging. Don't install this appliance in less than 12 square meters. Then the equations from the standard will tell you need 334 cubic meter per hour of airflow. And then you can start playing with, okay, but what if the air outlet of the unit becomes smaller? Because if it becomes smaller, I get higher velocity and better mixing. So you can play with that, and then you can see, okay, now you can use a lower amount of airflow. Right. So the idea here is just that this is a tool to help people evaluate which options are available for their design. And hopefully it's easier and quicker than if they have to do the Excel implementation themselves. So a couple of examples of what can be done with this new standard. For a floor-mounted air-to-air system, edition 6, for room sizes up to around 35 square meters, you are effectively limited to 152 grams of propane. And then slowly, when you get into really large rooms, you can go up around 200 grams. With the edition 7, you can already, in very small rooms, say 10 square meter, apply a fan and allow up to around 400 grams. And there are some other options. If you have larger rooms and don't want the circulation airflow, then you can apply enhanced tightness. Let's say you have 30 square meters, then you can go up around 250 grams. Simply by making additional design measures to ensure tightness. And maybe I should add that these additional design measures are actually already best practices for split systems. So it's not something that's going to be a big barrier for the industry, but it is something where we see a difference between what is best practice today and what was best practice 20 years ago when the original charge limits were written. Now, repeating the same exercise for wall-mounted system. Wall-mounted system, let's say 20 square meter, you'll be allowed around a bit more than 300 grams of refrigerant with the edition 6. With the new standard, you can get maybe to 450 just by doing enhanced tightness. And if you add airflow, you can go to a bit more than 800 grams. 800 grams, by the way, depending on how you optimize, can give you somewhere between 5 kilowatts and 10 kilowatts of cooling power without big problems. Ceiling mounted air-to-air system. Now, in a traditional system, you would be allowed around, or in the old standard, you'll be around a bit more than 400 grams for a 20 square meter room. And you can see, likewise here, enhanced tightness will give you an increase to around 600 grams. Adding airflow doesn't change that much compared to a wall mounted because you're mixing the whole room, so you still end up a bit more than 800 grams. Right, enough examples. Some other changes. There's no longer an upper limit on the number of refrigerant circuits in an appliance. So that means if you cannot get enough cooling power with the allowed charge limits, you can add more circuits because the charge limits only apply for each of the circuits. Sure, adding more refrigerant circuits in an appliance increases cost a bit, but it also expands what you're able to do. Then there are new options for showing that there are no ignition sources. This is to make it easier to go from a non-flammable to a flammable refrigerant. Then we have clarification of methods to avoid ignition sources. It's also to ease the transition. For some of these new architectures that we're going to see, people will not have a fan running all the time because it takes too much energy. So instead, they'll place a small refrigerant detector to activate the fan if there's a leak, or to close safety shutter valves if they detect a leak. And there we have expanded the requirements from 1.5 page to 10 pages. So it's almost a new gas detector standard, but it's customized to fit air conditioners and refrigeration appliances. And then we have a new method for verifying that it's located right, and a new symbol for room sizes. Okay, that said, remember, the task was not just to improve chart sizes. We actually got the task of publishing the new edition of the standard. So there are also a lot of other topics not related to flammable refrigerants, which has been updated and improved. So a little bit, before we go to the conclusion, I want to say a little bit about how is this applied in the EU. And in EU, we have two different ways of showing compliance with the Product Safety Directive. These safety directives is the European legislation requiring that products are safe. The first one is to comply with a harmonized standard. And that's a standard which is approved by the EU Commission. This new standard will become a harmonized standard, but this approval process will probably take 2 to 3 years if everything goes smooth. The other legal option in Europe is to apply a risk assessment, what is called an other specification. And that is already done on the IC 6335-2-89, where charge limit was increased from 150 gram of propane to 500 gram. So it's not unheard of, and you can do the same with this new standard. In reality, the technicalities of this are, there are a few details you need to be aware of. One is you typically don't apply this new standard for the complete appliance. What you'll do is you'll apply the current harmonized standard as far as possible, because then you cover most of the risks with a harmonized standard. Then you'll apply the edition 7. And in this case, in principle, you'll do it as far as possible. And normally that will handle your problems. There may even be types of appliances where you will have small things in the edition 7 where you want to do an additional risk assessment to deviate a little bit. But that's getting way too technical for now. The important thing is it can be applied, and if we look at how people have done with the -2-89, it's very likely that it will be applied if the manufacturers are forced to do so. So, conclusion. The new standard edition 7 was published here in May. It was a very long and quite thorough process, almost 7 years of work, more than 1,000 documents. The EN version will follow. It's probably going to take 2 to 3 years. The new standard increases the practical applicable charge sizes for all flammable refrigerants. And in particular for R290, you can get very close to the 988 grams indoors. Charge limits are linked to additional mitigation measures, and you have this Excel sheet you can use to evaluate whether you can use it in a given appliance. And by the way, I did say that indoors you can use up to 988 grams, but there is also a concept called a ventilated enclosure, which allows almost 5 kilograms, and that has been allowed for almost 20 years. So it also tells you a little bit that people will only change refrigerant if they somehow feel a need to do so. It's not enough that the standard allows it. Okay, the standard covers many other topics, and in EU we can apply it using a risk assessment approach. Okay, thank you.
Thank you very much, Asbjørn. This was quite encouraging to see that we delivered on our promise given during the adoption of the Kigali Amendment. Indeed, the safety standard, one of the key safety standards, has been updated and will effectively help with the implementation of the Kigali Amendment. If there are not any questions for clarification, we will have at the end the possibility to ask additional questions, make comments to the presenters. I do not see any request for the floor. Then we would have a closer look at the potential effects of applying the newly revised standard, and that will be presented by Irene Papst from HEAT, who will present the potential emission savings under the assumption that the safety standards will in practice be used. Irene, the floor is yours.
Thank you, Cornelius. Good morning, good afternoon, everyone. After all the technical details, I will give you a brief potential estimate on what the effect on HFC emissions could be between those two versions of the standard, the edition 6 and the edition 7 that Asbjørn also talked about in detail. Just need to figure out how I get my screen moving. What's happening now? That's how it goes. Okay, so I don't have to tell you anything about the Kigali Amendment. It's very clear that with the phase down of HFCs ahead of us, the servicing needs that will be arising from split ACs, the selection of refrigerants have to move earlier so that the servicing needs that lag behind are then actually coming down with the schedule. So of course, safety standards play an important role in the refrigerant choice, as Asbjørn also said, not only the standards, but it's an important part thereof. So what we did here is really a rather top-down estimate. We used sales projections of air conditioning equipment that was already developed by IEA, but also with GIZ and HEAT projections, for example, in the Green Cooling Initiative, and looked at the number of units that are going to be used in the future or projected to be used in the future up to 2050. And we can see here that the small and the medium-sized equipment is in terms of numbers in the majority. That's the greenish and the grayish colors, and also the bluish colors are still up to 5 kilograms HFC equipment. And if we look at that in terms of charge sizes and the refrigerant that is contained in that kind of equipment, that we can see, of course, the picture changes a bit, and that about 1/3 is contained in large size equipment, where also the newest editions are not so much a difference, but we can still see that 2/3 of that is in the small and medium-sized equipment, where the new standard actually makes a difference. So this is our assumptions here, and I have to give credit also to my colleague Daniel Coburn, who helped me with developing that part of that exercise. We used all those different subsectors of different AC appliances. You see here self-contained equipment, small residential split systems, and different sizes of split AC systems, and then also package systems and multi-split systems. We assigned an average capacity of that and used the factor to calculate the charge size of different categories of refrigerants. You see here A1, A2L, A2, and A3. And we also applied an average GWP of that refrigerant group. And where you see the green colors here, this is where the edition 7 actually makes a difference. Where you see 2 categories green, then we will assume in our models that both are used in equal terms. So you can see for the small systems, there is a potential to use A3 refrigerants, and for others, charge sizes are increased for A2L and A2 refrigerants. So for that little comparison, what we did is we put up one assumption, asking a question: what would be the effect on the emissions? And if from 2025 onwards, the lowest GWP refrigerant group, so A2, A2L, A2 and A3, that is allowed according to those two different editions would be used in new equipment. So we'll start with the edition 6, which is the previous version of the standard that was active before May 2022. And we look here at consumption, but the consumption in terms of CO2 equivalents. So that's why you can also see the red line, which is an estimated baseline. And we use two different examples. The left side is Article 5 countries, Group 1, and the right side is non-Article 5 countries, Group 1. So you can see when the, let's say, old version of the standard would be used as a basis for refrigerant choice, there's actually a problem getting down to the Kigali Amendment schedule. In order to, you can see in terms of what does that mean in terms of refrigerant quantities, you can see that there is a little bit of A3 in there for the very small systems like portable units and a bit of window units, but not much else. And the majority is taken up by A2L refrigerants, but their GWP limit, as you saw in the slide before, is not low enough to actually meet the Kigali schedule. So the same question is now, what would happen if edition 7 would be used as a basis for refrigerant selection? And you can see here there is a lot more room under the red line, and the chances to meet the Kigali Amendment from the unitary AC equipment part, of course, that's only on that here, is getting much better. So you can see that in terms of GWP weighted consumption, the consumption is going down tremendously. In terms of refrigerant distribution, what kind of systems are used, you can see that the A3 share is increasing a lot, but also A2L and A2 get a much higher portion of the whole refrigerant used. And that's why the overall GWP weighted consumption is going down. The most important question, of course, is also what that means in terms of emissions. And you can see here when we compare those different projections, you can see here in the orange line, the edition 6, and in the blue line, the edition 7, what that would mean in terms of refrigerant emissions up to 2050, that there is quite a big gap between those two. Then that translates to accumulated emission savings potential of 15 billion tons CO2 equivalents up to 2050. And I think this is a really a strong signal to actually work about standards and also work on more political signals to actually get those standards implemented. So that's a very small addition from my side, but I hope this is also showing what's actually in stake when working on standards. Thank you very much.
Yes, thank you very much, Irene, and to all presenters for having gotten up quite early this morning. And now they are still available for a round of questions, comments that you may have. So I would open the floor for any remarks, questions, and that our presenters and experts could answer. Since I do not see any requests for the floor, I would again so Ashley breaks the ice. Thank you.
Only as a personal individual now, not as a TEEP member. And with apprehension, because I'm not a super expert in this arena of safety standards. The critical question always is, okay, the theory's fine. What's the outcome in practice? Have there been any fires in refrigeration, air conditioning equipment? And is that related to the dose in practice? Is there a safe ceiling? I hope, I don't, maybe you all know the answer to that question and I don't. But that's my question.
Thank you very much. Indeed.
Because otherwise it's great.
Indeed, the last presentation was based on the maximum, on the best case scenario. Unrealistic to expect that as of 25, everyone would switch to the full to making full use of the new standards. But it shows the potential, and that was delivered. But I pass the question. Who wants to answer this question?
Actually, if I may, Daniel Colburn, who was the author of the first intervention, has an educated answer to this question. Of course, I cannot reply his answers, but he could reply to this question. I don't know if the colleague of Daniel Colburn, who made the first presentation, has any reply to this question.
So I pass the question to Britta Petzold, our first presenter. Please, you have the floor.
Yeah, it's a really good question, and we discussed it within the work of the LifeFront project when we had a workshop with the manufacturers on risk assessment. So what Daniel did in previous work is that he analyzed a little bit the risk from other appliances, mainly in the UK, and his, as you already said, so his assumption was the risk from the RAC HB appliances running on natural refrigerants is comparably low. So I would like to refer you to the work he did on this, because I don't have the numbers at hand right now, I have to admit. But he did some statistics and some analysis, and this was the outcome of his work. I'm happy to share the link to his work.
Yes. Maybe I should add that we have, of course, discussed exactly the same thing in the standardization committee. And the conclusion is that accidents are so rare that we actually don't have enough data. The accidents we hear about are typically accidents done by the installer, either because they treat the refrigerant completely wrongly, or well, actually, typically it's incompetence. Either that, or it's very, very large systems. So we hear about especially accidents on industrial-sized systems. And that's not so much related with flammability, but more with the toxicity, especially for ammonia. So I think the short answer is accidents are so rare that we actually don't hear about them.
Thank you. I see that Fabio still has the micro on. Do you want to take? Thank you. I had a request for the floor.
Hello, I was wondering if you have any information or have seen any risk analyses comparing the risks of using a heat pump that contains a flammable refrigerant with continuing to utilize methane gas or natural gas in heating equipment in residential homes.
I would assume that Asbjørn would volunteer to answer this question.
Yeah, or maybe Britta has some more comparative work. I don't have any numbers on it. My assumption is that the risk of using natural gas is significantly higher. And you can say, why all the fuss about safety standards if the risk of using natural gas is significantly higher? And the short answer is because we are not used to having this risk in air conditioners and heat pumps. So for us, it's a new risk, and therefore it's, or for our industry, it's a new risk, and therefore it is less acceptable than the risk from the gas industry, where they're used to this type of risk and now and then do have accidents. So you can say it's a weird thing, but our risk acceptance is much lower for the heat pump than it is for the gas burner.
Thank you. That's a quite remarkable answer and conclusion, but certainly right, because we all participate in the traffic, daily crossing roads, which is probably much more dangerous than heating with gas and using a heat pump with gas. Yeah, please, Bernhard, take the floor.
Thanks very much. Yes, I would have a question for Asbjørn. You said that as long as the EN standard is not published, so still in process, it's possible to use the IEC standard. Are there any strings attached? I see that industry is quite concerned about that and would not like to follow that path. At least that's my impression. Thank you very much.
There are strings attached. You can say the fundamental logic of a harmonized standard is that it is approved by the EU Commission. So if you follow the standard and your system somehow shows up to be dangerous anyway, then you can say, oh, well, I did not just the best I could, but I actually did what I was recommended by the EU Commission. And that will put you in a less, or that will reduce your legal risk, so to say. Once you're doing a risk assessment, then it is your assessment that the new standard is safer than the old one. And that means there's another element in your product approval that can be questioned. That said, risk assessments are actually very common in reality, but people typically don't know. And it's commonly used for other aspects than refrigerant safety. And as what we've seen with the -2-89, we see people actually using the new IEC standard. And it's actually not so much pushed by the bans on high GWP as it's pushed by the fact that if you use 500 grams in a very large display cabinet, then you only need one compressor, while the alternative is to use 3 or 4 times 150 gram, and that means 3 or 4 compressors, and that's more expensive. So yes, people do prefer to use the harmonized standard, but at the moment they can save money, then they are not so touchy about it anyway.
Thank you. Indeed, correct observation that the perception of the legal value of standards is sometimes not entirely correct. Seeing them as binding legislation, which they are not, but of course facilitating the approval process. Perhaps I can take 2 more questions, please.
Thank you, Thanawat Chunchaya from the World Bank. I'd like to ask about the maximum refrigerant charge level, the comparison between the IEC, this one, and the ISO 5149. which one is it at the same level or is it at the lower level? And if it's lower, then what would take precedent? Or, I mean, thank you.
Let's start with the first question. What takes precedence? And that depends very much on where in the world you are. The rule of thumb is that the IC standard takes precedent because that is more specifically targeted the product that you are concerned about. It's right now it's the IC standard that allows you the highest charge, and we are actually also in the process of updating the ISO 5149. And I'm pretty sure that once we reach the end of this update process, then the ISO 5149 will be the one allowing more charge, because we keep adding new mitigation measures and new concepts for reducing risks.
Thank you. Who has yeah, please, in the back. But you would need to come to the microphone that our experts can hear you.
Thank you for the presentation. I'm Hideki Kasaha from Industry Association of Japan. I have a question to the last presenter. I saw the slide showing the charge amount of the refrigerant for each flammable categories. So could you show this slide? Yes, thank you. So my question is, in principle, the charge amount of the refrigerant is pretty much rely on the the energy efficiency. Basically, if you need high efficient product, you need more refrigerant. So my question is, this assumption, what level of the energy efficient of the product is considered for this assumption?
That's a very good question. Honestly, I'm not a refrigeration technician myself, so I took the assumption that Daniel Colborn provided to me. So what we did, we have an average capacity here and applied 0.25 kilograms per kilowatt for the A1. And then we applied the correction factor that is depending on the density and the features of the refrigerant to reduce the charge sizes here in relation to the average capacity. Of course, that's very different that is a very top-down approach here and cannot take into account the very detailed design features of the individual system. So, as I said, this is a very top-down exercise showing the overall potential, what would be possible, and that's it. I don't go into very much detail here. So this is a very top-down looking at it. But if you want to get in touch in a discussion, what you think would be more fitting here, I'm very much open to also revise and do a second version, what you think would be more apparent.
Yeah, because as you know, there's another requirement on the energy efficiency, which is Eco-Design Directive. So, and also the Eco-Design Directive is going to be revised next year, and MEPS level will be increased. Then we're very much concerned about the limitation of the charge amount for A3 refrigerant can be enough for that, high level of energy class of the product. Thank you.
Thank you for this comment. In any event, if you have more detailed question later on, feel free to contact us. We will try to connect you with our experts, and with that, I would like to thank you for your presence, for your participation in the round of questions, and I would close the meeting with a applause for our presenters, and thanks back to Europe to them.